Okay, so I think we can start. So thanks for joining this container plumbing session. So this session is going to be about node resource interface, which allows to adjust the configuration of containers that are managed by a container runtime. And this session is going to be delivered by Krisztian and Peter. So a warm welcome for them, and I'm handing it over to you.
Thank you, Stefan. Hey, my name is Peter Hunt. I'm a senior software engineer at Red Hat. I work primarily on CRI-O, but also on upstream SIG-Node and sometimes Podman and Conmon.
Hello, my name is Krisztian Litkey. I work for Intel Finland as a Linux and cloud software engineer, contributing to CRI-O, Containerd, and NRI and a few other projects.
And today we're going to be talking about NRI, the node resource interface, with an introduction, some use cases, and some demos. Next slide, please. So an immediate question to be asked is, what is NRI? NRI was a project originally part of the Containerd project. It was proposed as a CNI, but for OCI specs, where there would be a mechanism to make modifications to an OCI runtime spec by a third-party plugin that could be plugged into a container manager, originally Containerd, and now also CRI-O. As of NRI 0.1.0, there's now a plugin mechanism and a framework for making these changes. The scope has begun as a unified way of exposing low-level plumbing to higher-level components through an interface common among two popular CRI implementations, Containerd and CRI-O. It allows admins to create extensions that hook into the lifecycle of both pods and containers and sometimes even make changes to those configurations. In short, NRI allows you to plug in an extra container customization logic into your runtime. It's your cluster plus your NRI-enabled runtime plus your NRI plugin means that you get your customization and your hook logic for your containers. Next, please. So here's a diagram of generally how NRI works. So we typically think of NRI now working in a Kubernetes context. Thank you. A pod spec comes into the Kube API server, which eventually makes its way down to the kubelet and then ends up as a CRI request to the container, the CRI implementation, like Containerd or CRI-O. Typically, without NRI, what Containerd or CRI-O do is then translate that OCI a CRI request into an OCI specification and pass that OCI specification down to the runtime. But NRI allows for the a plugin to hook into different pieces of those steps. So instead of the CRI implementation immediately translating in the OCI spec, it takes some information and like some of the spec and passes it down to an adaptation layer within itself. And that adaptation layer calls over a socket to talk to NRI plugins that that can take action at certain points in the container or pod's lifecycle, as well as make some modifications depending on which field in the OCI spec. Eventually, once those plugins are done, that passes back up through as in a reply to the adaptation layer, which then goes back up to the implementation, which then continues on as normal and passes that down as an OCI specification, or it takes its own action in terms of what the event actually was. Next, please. Zooming in a little bit closer, so the NRI has a number of protocol definitions, and then each of those are related to a lifecycle event inside of a container or a pod. So you have container start, create, update, stop, remove, and then a bunch of post operations like post stop that allow you to respond after something has happened. Each of those inside of the CRI implementation has an NRI hook that calls into the adaptation layer, and that adaptation layer calls a specific TTRPC call down to the down to the plugins. The plugins are they're able to be multiple plugins. So, and then they chain. So the first CRI plugin that the adaptation layer finds will take the spec, possibly make modifications if that's allowed, do its work, pass that along to the next one, and it goes all the way up until finally the response comes back to the adaptation layer and back up to the runtime. Next, please. So digging in even deeper, so NRI basically has three pieces to it. It has the client, which is the adaptation layer that each of the Containerd and CRI-O have vendored in and call into each. So in each of the CRI calls, there is a specific call down to the NRI client that will trigger the NRI process. And sometimes you pass the OCI spec, and sometimes you're just saying like, hey, this pod is stopping. What do you want to do? Plugins. Then the NRI protocol is the way that the adaptation layer actually talks to each of the plugins. And this is a protobuf-based API with TTRPC bindings. And it uses the lifecycle event request execution model. So the plugin will call into each of the adaptation layer will call into each of the plugins when certain lifecycle events happen. For containers, you're able to make some modifications to the OCI spec. But because pods don't have as clearly a relationship with that, it's not necessarily, you're only like hearing when a pod is created most of the time. But some fields in the OCI spec for containers can be adjusted by an NRI plugin. And if there are conflicts between different plugins, the call errors out. And then finally, there's some bootstrapping code that plugin stub that allows, for some of the low-level plugin logic to be taken care of by a library. So plugin authors can focus on the pieces of work that they need to do, like actually be modifying the spec or responding to an event. So all these things together make an ecosystem that allows for, container runtime implementation agnostic, changes or events based on container and pod lifecycle events. So I'm going to pass it off to Krisztian, who will take us on a journey of what we can do with NRI.
Thank you, Peter. So what can I do with NRI? Or actually, what can my plugin do with NRI? So NRI exposes your plugin to the full life cycle of events of pods and containers. For pods, this is run, stop, remove pod sandbox. For containers, it is a create, start, update, stop, remove container, and a few post variants, post create, post start, and post update. So this already allows you to track the state of the pods and containers accurately through the NRI interface. In addition, NRI also allows container customization in response to 3 lifecycle events: create container, update container, and stop container. During container creation, a subset of the OCI spec parameters can be adjusted. For the other events, update and stop, only the resource-related parameters of a container can be updated. So inputs. So for every event, lifecycle event, you get basically a bunch of data about the pod or container that the event is related to. You can use this input to decide how your plugin is going to respond to the event, if it needs to respond at all. For pods, you get basically pod ID, name, UID, namespace, labels, annotations. Then you get Linux namespaces, cgroup, fspass, runtime handler, resources, resource overhead. For containers, you get the pod that the container belongs to, container ID, name, labels, annotations, Linux namespaces, cgroup, fspass, the command, environment variables, devices, mounts, OCI hooks, and resources. I might have forgotten some of the input that you get, but best is to check from the actual protocol. So outputs. So the event responses are the outputs that the plugins use to customize containers. So during creation, you can adjust containers annotations, environment variables, mounts, devices, OCI hooks, and resources. For already created containers, you can only update its resources, which basically includes scheduling parameters, CPU and memory pinning, memory and huge page limits, last level cache allocation, block IO throttling, and then is C group V2 parameters. So I have a bunch of demos, but there is just no way that I can squeeze all of them into our time slot. So what I will try to do, I will try to show you a really simple one and a really complex one, a little bit rushing through the demonstration for those, and then hope that we will get a few more minutes in the end for questions and answers. So the simple plugin is basically an annotated device injection, and the complex plugin is basically a full-fledged Kubernetes resource management plugged into the runtime using NRI. So let me switch to my demo environment. Here. So basically, I have a single node cluster set up. It's running CRI-O 126.2 and it's running Kubernetes 126.3. I have already NRI-enabled in CRI-O. I have loaned basically the NRI repository, which has a bunch of plugins, and I compiled. Okay, so and I have compiled. So here are those plugins, and then I have a few demos here. So I will demonstrate this first, this annotated device injection. This is very simple. So basically the plugin hooks itself into container creation. It looks at the annotations present on the pod. And then if there is a particular key, then it interprets that annotation as a device injection request, and it injects based on that device to the container. So I can show you how my test pod looks like. So here you can see that there is annotation for 3 containers, C0, C1, C2, and those are basically injecting just some fake devices. First one gets one device, second another one, and the third one should get both of them. And then I had correspondingly named containers. So I will start up the plugin here, and then I will create a test pod. Okay, and then I have a script here. Basically, kubectl executes one by one into each container and then lists the devices. So I can show you what happened. So we can see that this really happened. So the first device, well, the first container got injected with so according to the device in the annotation, the second one as well, and the third one. So that was a fairly simple one. So let's remove this pod, and now I can switch to the complex one, which is actually much more complex. So basically here I have a daemon set. So this plugin is going, the first plugin I was running by hand. This one I will basically deploy as a daemon set. So this is much more similar to how you would deploy basically a device plugin into Kubernetes. And this plugin implements a reasonable default resource allocation policy. Basically, what it tries to do automatic resource alignment and workload isolation. So I have a cluster, or I have a node here, is having several NUMA nodes, and then I have a, and this policy is basically, we call it topology aware because it does the workload isolation so that it detects the underlying hardware topology and tries to basically place workloads into different topology zones on the hardware so that those are interfering with each other as little as possible. So I can show you my test pod. My test pod has 3 containers. It's a guaranteed QoS class pod, and it is so that one of the containers is eligible for exclusive CPU allocation. So I can show you what happens if I run this pod without the policy deployment being in action. So if I just say okay, so it's running. I have a script here which basically finds out, so one by one it goes through also all the containers, and basically from proxel status, so it kubectl XX into the container, and then from proxel status it basically reads out the CPU on memory pinning. So I can show you what happens here. Actually what I had, so I already have this policy running. So my demo was demonstrating what happens when the policy is already running. So you can see that the first container got a shared allocation, but it got pinned to NUMA node 1. So it got isolated there. The second one got assigned to NUMA node 2, and the third one to NUMA node 3. And the second container also got an exclusive allocation because it was eligible for that. Now I can try to show you what happens if this policy would have not been running. I wanted to do it the other way around, but I forgot that this was already running. So delete the pod. And I delete also the policy. It's not there. So now if I apply again pod and try to read out the resources, so now you see that what happens. So basically my cluster is running without any policies enabled in kubelet itself. So it has the non-CPU policy. Because of that, all the containers end up running practically spanning all CPUs and all memory nodes, so all NUMA nodes. So actually, because I made this mistake and I demonstrated this in the wrong way around, now there is one more thing I can show you. So this policy works so that when it starts up, so NRI provides an initial synchronization mechanism when the policy starts up, or when a plugin registers, it gets a full dump of existing pods and containers. And this policy works so that in response to that synchronization, it will reassign resources of these containers. So in a way, it tries to get itself into a sort of acceptable initial state as if it would have been running already when those containers were created. So let's try this in practice. Not something that I was planning to demonstrate, but now I will hope that it works. So I started it up. So let's see how this now looks like. Yeah. So basically it changed the allocation, reallocated the resources of the containers according to its own invariant condition that it tries to always maintain. I think that's it that I wanted to show about this. So I have a few more slides, and then we can have a Q&A session, or if there is time, then there are a couple of, I can try to show a few other demos. Let's see, stop sharing. So I will switch back briefly here. Okay. So this is basically a brief summary of this last demo that I showed. So plug our resource policy in the runtime. So basically, this is a repository that we recently open sourced. So a repository which has basically a recently open source set of policies, 2 of them that we implemented. And I was showing this topology where the whole thing is set up so that it works pretty much like a device plugin. So Kubernetes daemon set, you can configure policies via config maps, exposes node resource availability using the node resource topology CRDs. And this whole thing is set up so that basically it internally has an abstraction which is built on top of NRI, which is geared towards resource management. So it is a higher level abstraction. Instead of a create container, start container, stop container, you are getting an abstraction which basically consists of 3 calls: allocate resources, update resources, and release resources. That's it. So current and future work. So NRI is currently experimental. And because of this, it's disabled in both runtimes by default. So one of the things that we are working on, we are trying to chop away one by one the reasons behind this experimentalness. So basically fix any bugs that we find, have better test coverage. About the NRI protocol, we try to make sure that it's functionally both complete and correct. Provide better documentation, maybe improve the protocol. We have some ideas how we could make it more efficient. And also that we have some ideas how we could share a little bit more code between the runtime integration bits. Then there have been some folks have approached us with ideas about potential new or sort of scope additions to NRI. So one of those is related to CNI networking, another is image service. So maybe something will happen also on that front. And we just opened this community maintained NRI plugin collection. I have a link to it in this presentation, and actually this last demonstration was coming from that repository. Yeah. So questions, any questions, comments, anything? Or would you want me to try to demonstrate another? So this slide, so here you see this GitHub repository. This GitHub repository has basically a copy of this presentation. I will also include a link to the, because that's a PDF version, but I will also include a link to this Google Docs version. So if you want, I can show another small demo, because I have only been talking about.
I think it would be nice.
Okay, Michael Brown is here, so I feel obliged to also show you something about Containerd. So let me stop sharing this and then try to share a window, and I have another test environment set up here. So I have also a single, can you see my screen?
Yeah.
Okay, so I have another cluster, single node cluster set up similarly. It's running Containerd 170.
Could you make the text a little bit larger?
Is it any better?
Yeah, it's a little better.
So what I could show you here is that so we have one specific plugin that we wrote with Containerd in mind, and that's actually an OCI hook injector. So Containerd doesn't natively support OCI hook injection, but if you enable NRI support in Containerd and you install this plugin, start it up, then you should have working OCI hook injection. So I have a few hooks already put in place. I can show you. etc. I have 2 hooks basically. One which is always injected, and it's injected if, okay, this is always injected, and I have another one, which is only injected if the process running inside the container is busybox. And it is, these hooks are for press start and post stop. And basically I have, so the hook is actually a user local admin demo hook. So I can show you, what that does. So it just logs and then touches a file in the file system. So what I can do is that I will remove this TMP demo hook. Yes, then I can do a tail. Demo hook log. Yeah, it's not there. So, and then I have a test pod. Two containers, one is busybox and the other is shell. Most of them are busybox. One is calling itself shell, the other is busybox. So for one, you should get only the always inject hook effective. For the other, you should get both. So let's see what happens if I apply this without the hook being in place. I hope I don't have the, yeah, okay, I don't have the hook. So nothing should happen here. Running, no hooks got executed, but if I now run the hook injector and recreate this whole thing. So what happened is that basically it ran for both containers, and I think I have a, I don't have it. I could try to look into the container what happened, so whether it's really test box. Test pod. We should see that basically, yeah, so the demo hook was executed in the namespace of the container and it was touching that in place. So it was working. So this is one thing that I wanted also to show you. So you can see that basically we also have, so whole mechanism, same mechanism works also in containerd. Actually, if I had a little bit of time, we have 2 minutes, so I could show you that if I plug in the same resource policy, maybe I can try to squeeze that in. So I can try to say that apply. This one. So I can run the exact same policy that I was running in the other one, so in CRI-O, and I can do I have the wrong test pod, but I can run now this test pod for the this one, and I can see how it allocated. So we get the same allocation here. So actually the very same code is now running in CRI-O and containerd. So sort of proof that those are close enough, even if they are not working necessarily fully identically. Yes. So
very nice. Thanks, guys, for the presentation. Maybe there's a little bit of time for more questions. And we can open the floor for questions if you want to ask them in the chat window. Otherwise, we will thanks our guest speakers today. Thanks for the nice session. And we invite you to join the next one, which is about Windows containers, the forgotten step shield. So thanks both Peter and Krisztian for this introduction.
Thanks for having us.
NRI. So thanks everyone.